Welcome back to TechTide Digital Lifestyle, and congratulations on reaching the final episode of our Alternator Masterclass series. In this lecture, we are diving deep into the brushless excitation system, one of the most critical components of modern alternators used both in marine ships and industrial power plants. Before starting, watch this tutorial. Please subscribe TechTide Digital Lifestyle channel and don't forget to like this video and comment and share. As you can see on the slide, the 3D alternator with a glowing protective shield symbolizes the importance of continuously monitoring and safeguarding the alternator against electrical, mechanical, and thermal faults. Unlike traditional brush-type exciters that use brushes and slip rings, brushless exciters remove all these components. This makes the system virtually maintenance-free, more reliable, and safer to operate in harsh marine environments. By the end of this lecture, you will understand the working principle, main parts, diagram interpretation, automatic voltage regulation, common faults, and practical troubleshooting methods. For marine engineers and ETOs, this knowledge is essential because brushless systems are standard in modern diesel generators. It's also vital for B.Tech graduates, industrial engineers, and anyone preparing for marine electrical exams. Pay attention to the slide graphics showing the alternator in motion. Notice the flow of energy from the exciter to the rotor. This visual will help you understand the concept as we break down each component in detail in the following slides. Brushless excitation ensures that your generator operates smoothly, even under load variations, extreme weather, or high-speed shaft rotations. Brushless vs brush-type excitation. On this slide, we compare the traditional brush-type excitation system and the modern brushless system. Notice the side-by-side 3D graphics, one showing brushes and slip rings in the conventional system, and the other showing a rotating rectifier and AC exciter in the brushless design. In brush-type exciters, brushes maintain contact with slip rings to deliver DC to the rotor field. While this works, it causes friction, wear, and sparking. Maintenance is frequent, and operational reliability decreases over time, especially in marine applications where vibration, humidity, and saltwater can worsen wear and corrosion. The brushless system, by contrast, eliminates brushes and slip rings entirely. AC generated by a small exciter mounted on the rotor is converted to DC by a rotating rectifier assembly and fed to the main rotor field. This system is cleaner, safer, and requires very little maintenance. The graphics also highlight how energy flows smoothly from the exciter to the rotor, without friction or sparking. Brushless systems also improve efficiency. Without brush losses, the alternator maintains a more stable voltage under load variations. This slide also shows the advantages clearly: long service life, reduced maintenance cost, cleaner operation, and better reliability, all essential for continuous marine and industrial operations. Engineers can see why almost all modern high-speed alternators now use brushless excitation. Basic working principle. This slide shows the working principle with a 3D schematic. Notice how AC is produced in the exciter, flows to the rotating rectifier, and energizes the main rotor. Step 1. The AC exciter, mounted on the alternator shaft, produces alternating current proportional to rotor speed. Step 2. This AC passes through the rotating rectifier assembly, which converts it into DC. In the graphic, red arrows represent the AC flow, and glowing yellow arrows show DC after rectification. Step 3. The DC energizes the main rotor's field windings. The rotating magnetic field induces voltage in the stator windings. The animated 3D flux lines on the slide illustrate this magnetic flux clearly. Step 4. The induced voltage in the stator is supplied to the load. Meanwhile, the AVR monitors the voltage and adjusts excitation to keep it stable. This slide emphasizes the seamless energy flow and shows why brushless systems are self-contained. Unlike brush-type systems, no external DC supply is needed. The 3D graphics reinforce understanding by showing current paths, rotor excitation, and induced voltage visually, making it easier for students to remember for exams or practical marine. Main parts or definitions. Here, the slide shows the main components of a brushless excitation system in detailed 3D view. AC exciter generates AC current. You can see the rotating coils highlighted in blue glow in the diagram. Rotating rectifier assembly, RRA, converts AC to DC. Observe the diode bridges in the animation and the glowing yellow arrows showing DC flow. Main rotor creates magnetic flux. Notice how the flux lines in red extend into the stator windings. Pilot exciter, if included, provides a reference voltage for accurate AVR operation. AVR automatically adjusts field excitation to maintain output voltage. This slide emphasizes not just the component names, but their functional roles. The 3D graphics help visualize energy conversion, from AC in the exciter, rectified to DC, to energize the rotor and induce voltage in the stator. Understanding these parts is critical for troubleshooting. For example, if DC is missing at the rotor, the problem could be in the RRA or exciter. These visuals help marine engineers and ETOs locate and diagnose faults efficiently. For exams, memorize not just the names, but also how they interact in sequence to produce controlled voltage. Diagram of brushless excitation. On this slide, we have a detailed 3D diagram of the entire brushless excitation system. Observe the labeled components: AC exciter, rotating rectifier, main rotor, stator, AVR. Each arrow represents the flow of energy and magnetic flux. Blue arrows indicate AC current from the exciter. Yellow arrows indicate rectified DC to the rotor. Red flux lines show magnetic field generation. Notice the feedback loop from the stator to the AVR. The AVR senses output voltage and sends signals to adjust the rotor field automatically. This visual reinforces the step-by-step working principle explained in the previous slides. This diagram is particularly useful for marine engineers because it shows exactly how energy flows, how excitation is generated, and how voltage is regulated without any brushes. It also serves as an exam diagram, be able to label every component and describe its function. During troubleshooting, visualizing this diagram helps locate faults such as rectifier diode failure, exciter winding issues, or AVR malfunction. Step-by-step working explanation. Now let's break down the working of the brushless excitation system step by step, with reference to the 3D graphics on your slide. Notice the flow of AC current from the exciter, shown by the blue arrows, which passes to the rotating rectifier assembly highlighted in yellow. Step 1. The AC exciter mounted on the alternator shaft generates alternating current as the shaft rotates. This AC voltage is proportional to the speed of the shaft, and the exciter is mechanically coupled to the main rotor. Step 2. The generated AC flows into the rotating rectifier assembly, which converts it to direct current. The diode bridges in the RRA are highlighted on the slide in glowing orange, showing how they rectify the AC into pulsating DC. Step 3. This DC is then fed into the main rotor field winding, which creates a rotating magnetic field. Observe the red magnetic flux lines in the slide. These lines move in synchronization with the rotor rotation and induce voltage in the stator. Step 4. The stator windings pick up this magnetic flux, generating three-phase AC output. The output voltage is sensed by the AVR, which continuously adjusts the rotor field to maintain a constant voltage despite load fluctuations. Notice in the graphics how all these components work in perfect coordination. The exciter, rectifier, rotor, stator, and AVR form a closed-loop system. This stepwise flow is essential for troubleshooting and exam preparation. Understanding this flow helps you quickly identify where faults may occur and how energy is transferred in a brushless excitation system. Automatic voltage regulation, AVR. The automatic voltage regulator, AVR, is the brain of the brushless excitation system. Take a look at the slide graphics. The AVR is connected to the stator and rotor, with feedback loops clearly illustrated using animated arrows. The AVR continuously monitors the stator output voltage. If the output drops below the desired value due to load increase, the AVR increases the DC excitation to the rotor. Conversely, if the voltage rises above the set point, it reduces the excitation. This keeps the alternator voltage stable and prevents damage to connected equipment. The slide also shows the AVR controlling excitation in real time with glowing control arrows. In parallel operation of multiple generators, the AVR ensures proper load sharing, avoiding overload on one generator. For marine engineers, this is critical. Sudden load changes, such as starting large pumps or motors, could cause voltage dips or spikes. The AVR compensates automatically to keep voltage within safe limits. Notice how the graphics visually demonstrate this feedback loop and how minor voltage variations are corrected immediately. This slide is essential for both understanding system operation and preparing for exams. Troubleshooting common faults. This slide focuses on troubleshooting, a key area for practical marine engineering and exams. Notice the 3D graphics highlighting the rotor, rectifier, and AVR, with red warning icons representing faults. Common faults include 1. Over-excitation, high voltage caused by AVR failure or control wiring issues. Can lead to rotor overheating and insulation damage. 2. Under-excitation, low voltage due to rotor field failure or exciter issues, causing poor load sharing. 3. Rectifier failure. If a diode fails, DC supply to the rotor is interrupted, and the generator cannot produce rated voltage. 4. AVR malfunction causes fluctuating voltage, unstable frequency, and may trigger alarms. Notice how the graphics allow you to visualize fault locations. For example, red flashing on the rectifier diodes shows where current flow stops. Troubleshooting involves stepwise checks. Measure output AC, check rotor DC voltage, inspect rectifier diodes, and verify AVR response. Following the flow illustrated in the graphics makes fault detection faster and more accurate. For exams, focus on fault causes, indicators, and corrective actions, as these are frequently asked in oral and practical assessments. Importance or safety features. This slide illustrates why brushless excitation is preferred in modern alternators. Notice the graphics showing a high-speed marine alternator operating with no brushes and glowing arrows representing smooth energy flow. Key points. Maintenance-free operation. No brushes means no friction, sparking, or frequent replacement. High reliability. Continuous operation without unexpected shutdowns. Safety. Eliminates fire risk from brush sparking. Efficiency. Stable voltage ensures proper operation of all electrical loads. Load sharing. Critical in ships where multiple generators operate in parallel. The 3D graphics also highlight cooling channels, rotor integrity, and magnetic flux, showing how mechanical and electrical safety is integrated. In marine engineering, downtime is expensive. Brushless excitation minimizes downtime while improving system reliability. From a practical standpoint, this slide reinforces the importance of preventive maintenance, monitoring sensors, and the role of AVRs and PMS. Understanding these features is crucial for engineers who operate high-speed alternators and for those preparing for exams. Summary or exam focus. Let's summarize the brushless excitation system. On the slide, we see a checklist with the main points. Working principle. AC exciter rotating rectifier DC rotor field induced stator voltage AVR feedback. Main components: AC exciter, RRA, main rotor, pilot exciter, AVR. Advantages: brushless, maintenance-free, reliable, safe, efficient. Troubleshooting: under-excitation, rectifier failure, AVR malfunction. Practical importance: marine, industrial applications, load sharing, voltage stability, safe operation. The 3D graphics reinforce energy flow and component interaction. For exams, focus on labeling diagrams, explaining working steps, and describing troubleshooting methods. For practical marine engineering, understanding these details ensures efficient operation and fault diagnosis. Remember, brushless excitation is not just theoretical, it's applied in almost all modern marine and industrial. Thank you for watching video 10 of the Alternator Masterclass on TechTide Digital Lifestyle. This concludes our complete series on alternators, covering theory, parts, practical applications, troubleshooting, and exam-focused questions. If you found this lecture valuable, please like this video, subscribe to the channel, and comment your doubts or questions below. Share it with fellow marine engineers, ETOs, and industrial electrical engineers who want to master alternator systems. In addition, don't miss our final review and numerical session coming next, where we revise all 10 videos, solve important numericals, and cover key interview questions. Stay tuned, keep learning, and become confident in electrical engineering.